Okay, so we are ready to start chapter 4. This is our last chapter for the course. And this chapter starts off talking about exponential functions. And as we go through the chapter, we're going to do a lot with exponential functions and something called logarithmic functions, and we'll look at how they relate to each other and how we can use them to solve some problems. In this first section, though, we're just looking at exponential functions and their graphs, and then we're going to look at a couple of applications. So the first thing I want you to do is to have some basic idea of what an exponential function looks like when you graph it. They're always in the form f of x or y, of course, equals b, which we call the base, raised to the x power. So b is some constant raised to the x power. Notice this is different from a polynomial. When you have a polynomial, the variable is your base and it's raised to a number. When we work with exponential functions, the base is the number and it's raised to a variable power. So what does the basic graph look like? Well, if we make a kind of a quick sketch here just to have in our notes, these functions are always going to be an increasing function. They go through 1 on the y-axis, and then they're increasing just like this from left to right. The basic function looks like this. Now, there could be some shifting and some things that are going to affect the way this looks, but the basic shape looks just like this. So if this is of course, my x-axis, this is my y-axis, I want you to think about what the domain would be for this function. So you notice that we've got arrows on both ends. So this goes out in the x direction to negative infinity, and up, it keeps going up, but it also keeps going out in the positive x direction to positive infinity. So our domain here is negative infinity to positive infinity. How about the range? Range, remember, are all your y values, so think low to high. The lowest y value on this graph, it never crosses the x-axis. In fact, it never touches the x-axis. So it does not go below 0, and then it goes up to infinity. Remember, infinities, when we write in interval notation, always take parentheses. The 0 is also going to take the parentheses here because it never actually touches the x-axis, so it does not include 0. The y-intercept, this always goes through 1 on the y-axis, so the y-intercept is 0, 1. X-intercept, remember we just said it never touches the x-axis, so there is no x-intercept. There is a horizontal asymptote. Remember at the end of chapter 3 we talked about horizontal and vertical asymptotes. So this does have a horizontal asymptote. As x goes out to negative infinity, the graph levels off at the x-axis, so that means that y equals 0 is our horizontal asymptote. Vertical asymptote, there is no vertical asymptote. It just keeps going up, but it's never bounded by anything vertically, so there is no vertical asymptote. Now, as long as the base is a number greater than 1, then the function is going to look like this, and it's going to be an increasing function. You notice that this is increasing the entire time. If, however, the base is a fraction between 0 and 1, the function is going to change to decreasing. And I'll show you an example of that in a few minutes. But that's what you want to look at. Is if the base is a number between 0 and 1, it changes to a decreasing function. And we'll look at an example. The transformations and the shifting are very similar to what we had back in chapter 2 when we talked about the parent graphs and we talked about different types of shifts. If there's a number added or subtracted on the outside of the function, that shifts the graph up or down. That's a vertical translation. If we have a number added or subtracted to the inside of the function, so in other words, in with the exponent, that's going to be a horizontal translation, and it shifts left and right. And you may or may not remember back to chapter 2, we said horizontal translations were opposite whatever the sign is. So in other words, if it's plus a number, it actually moves left. If it's minus a number, it actually moves to the right. And we'll do some examples of this as well. If there's a negative in front of the function, just like in chapter 2, it reflects the graph over the x-axis. So it flips the graph over the x-axis. If there's a negative in front of the x, it reflects the graph over the y-axis. If the base is being multiplied by a constant, remember exponent rules, the c and the b here, that they cannot be multiplied. But let's say you had b to the x multiplied by a 2 or 3 or something in front. It stretches the graph if c is greater than 1, and it shrinks the graph if c is between 0 and 1. We're not going to do a lot of these. The main thing I want you to notice with these, though, is that it changes the y-intercept. And we'll do some examples of this in class as well. So let's look at some basic practice here. So graph the function 2 to the x. So our basic exponential function, the base is 2. Notice that is a number bigger than 1. So it's going to be an increasing function. There's no shifting, no reflecting or anything. It's going to go through 1 on the y-axis, and it's going to look just like this. The difference between a base of 2 and a base of 3, for example, has to do with how steep the graph is. We're just going to be keeping our sketches really simple. We're not going to worry too much about the steepness. But if you wanted to observe the steepness, the difference here, so if this is f of x equals 2 to the x, I'm going to label that f of x. G of x equals 3 to the x is going to go through 1 just like the first one did on the y-axis, but it's going to grow at a little bit of a faster rate, so it's going to be a little bit steeper just like that. Everything else stays the same rather, so there's our g of x function. Now, how is h of x going to shift? It's going to take that g of x function we just had, it's x plus 1 in the exponent position, so that's going to be a horizontal shift, left, right, and because it's plus 1, remember we said horizontal shifting is actually opposite, so plus 1, it's going to take this y-intercept point and it's going to move it to the left, 1 unit. And I know my graph's getting a little jumbled up here, so try to do the best you can. Take this point you had on your y-axis and just literally shift it to the left 1 unit. And that's going to be your new h of x function. Nothing else changed though. I didn't shift it vertically, so the horizontal asymptote is still the x-axis, and that's pretty much it. Let's try the next one. 4 to the x. So the 4 to the x is just your basic increasing function. It's going to be a little steeper than the others we had earlier, but again, I'm not looking at how steep you make it, so don't worry about that as long as you have the right shape. Now, g of x equals 4 to the x minus 3. Notice where that minus 3 is. It's not in the exponent position, so this is going to be like this. So it's going to be a vertical shift. It's not opposite like the horizontal shifting is, so minus 3 is going to move the graph down 3 units. So you're going to take that y-intercept point and you're literally going to count down 1, 2, 3 units. So now the y-intercept is at -2. And so there's our g of x graph. When it shifts vertically, there is also a shift with the horizontal asymptote. So the horizontal asymptote, remember, it was at the x-axis. If I move the graph down 3 units, it's now going to be at y equals -3. So if that horizontal asymptote shifts, go ahead and label that as well. Okay, let's take a look at example 3. So now we're looking at the graph of the function y equals 1/2 to the x power. So what do you notice about the base here? The base is a fraction less than 1, right? So we said just a couple minutes ago that if the base is a fraction between 0 and 1, instead of increasing, it's going to be a decreasing function. So how does that apply to this question? So our base is a fraction between 0 and 1. It's still going to go through 1 on the y-axis. That is not going to change. But instead of going increasing from left to right, it's actually going to be decreasing. So it's going to look just like this. And there you go. So that's our y1 graph. It's decreasing from left to right. Now the y2 graph, it's 1/2 to the -x. So when the x is negative, take a look back at your first page, your translations. When the x is negative, it takes the graph and reflects over the y-axis. So that's going to take the graph we just drew, same base, and it's going to reflect over the y-axis. So it's going to flip it this way. The point here is not going to change, but think about, can you visualize if you take this and you flip it over the axis, what that's going to look like? It's going to look just like the increasing function we had earlier. So this would be y sub 2. And if you think about exponent properties, that should make sense, because 1/2 to the -x, remember the rules with exponents, when you have a negative exponent, we can flip it, and that makes it a positive exponent when we do that. So this is really the same as 2 to the x, which is like what we had earlier, right? A base that's greater than 1 would be an increasing function. So there you go. The last graph we're going to look at uses e. E is the natural exponent. It's an irrational number, kind of like pi. It just keeps on going forever in both directions. If you have your calculator or your graphing calculator, which you're actually going to need for the next example anyway. Go ahead and get it out and take a look at the E key. I've got a scientific calculator here. It's kind of hard to see, but I've got a scientific calculator here. And in my calculator, you might have to find it on yours, my E key is right there above the LN key, which we'll talk about in the next section. But the E key is this irrational number that we're talking about. If I want to see what that's equal to, I'm going to put a 1 in because I want it just to the first power. I just want you to see the number here. There it is. So E is equivalent to the number 2.71828, and it just keeps on going forever. So what I want you to remember is that E is around 2.7. You don't have to have any of it memorized or anything like that, but it's a number that's bigger than 1. So E is a special base, in other words, that's a little bit bigger than 1, 2.718 we said, right? So as long as the base is greater than 1, the graph is going to be an increasing exponential function. So here, let's do this. I'm going to graph just e to the x first. So no shifting, forget the minus 2 for a minute, just e to the x. So here I'll call this y sub 2, we'll call it e to the x. And that's going to look just like all the other exponential functions. They're all really similar. We're not worried about steepness. So there's the e to the x function, just like everything else, because the base is greater than 1, it's increasing. Now, how is that minus 2 going to shift the graph? It's on the outside, so it's going to move it down 2 units. So you're going to take the y-intercept, you're going to go down 2 units and put a point right there. And so here's the graph for e to the x minus 2. Now, what else shifted because I moved it vertically? The horizontal asymptote. So remember, it was originally at the x-axis. If I shift it down 2 units, now it's at the line y equals negative 2. The last thing in this section I want to look at are a few applications of exponential functions. So this first section here talks about investing money. And sometimes we'll see some questions where we talk about if we take money and we invest it and it's compound, the interest compounds. Every so often, if you have a bank account, for example, you'll notice that if you look at your statement at the end of the month, even if it's a digital statement, they'll say you got some interest in your account, your bank account, your checking account. It's not going to be very much, but maybe a couple pennies a month. But either way, every month it compounds. They take what's in your account and they tack on interest. So when we talk about compounding interest, that's what we mean. And so we have 2 equations we can use to look at how much money we would have in an account, an investment, if we let it sit in the account and let the interest accrue. So it says the total amount of an investment A, so A is the amount of money we're going to have after a certain time period, accruing interest compounded n times per year. So remember what these variables mean. N is the number of times per year the interest is compounded. The formula for this is A equals P times parentheses 1 plus R over N, close parentheses, to the NT power. P is the principal. Principal is the original amount that you started with when you started investing. R is the annual interest rate, and it has to be in decimal form. N, we said, is the number of times per year the interest gets compounded. So like if it's your bank account, it's compounded monthly, that would be 12 times per year. Quarterly would be 4 times per year. Trying to think, daily, I guess, would be 365 times a year, and so forth. And then T is the number of years we let the money sit in the account. The other type of compound interest we might see is continuous, compounding continuously. And so if something's compounded continuously, we use this formula, A equals P e to the RT. P is still your principal, R is still your interest rate, T is still your time, but compounded continuously means always, all the time, the computer is just continuously compounding interest on the account. So they use E, which was that same E that we talked about earlier up here. So let's look at some examples. It says you decide to invest $8,000 and have the choice of 2 investment options. One pays 7% compounded quarterly. The other pays 6.5% compounded continuously. Which will be a better investment after a 5-year period? So in other words, if we take our $8,000 principal and we want to invest it and we want to make the most interest possible, which investment should we go with, the first option or the second option? So the first option, it says compounded quarterly. So when they say quarterly, monthly, annually, daily, whatever, that's n times per year, we're going to use this first formula. So here, let's write some things down. So for option 1, we're going to use that first formula. And so P, of course, is $8,000. What else do we have? R is the interest rate. So they told us in that first option it's 7% interest, and I need that as a decimal, so I'm going to put 0.07. N is the number of times per year, so if it's quarterly, that's 4 times per year. And T is the number of years we're going to let it sit there. Both investments we're going to let sit there for 5 years, so T is 5. So if we put this together and put this into our formula, we want to calculate A at the end of the 5 years. How much do we have? We're going to do 8,000 times 1 plus 0.07 divided by N, which was 4, to the NT power, so 4 times 5 power. Now, the hardest thing about these questions is putting them in the calculator correctly. If you have a graphing calculator, you can probably go ahead and just plug everything in, and the calculator will take care of everything for you. Here's my old TI. I'm not sure how good this is going to show up for you, but let's see. So if we put all the information in, I'm going to do 8,000 parentheses 1 plus 0.07 divided by 4, close parentheses, caret key, so raise it to it was the 4 times 5 power. You need parentheses for the 4 and the 5. So I'm going to do parentheses 4 times 5, close parentheses. And at the end of that 5-year period, we'll have $11,318. Okay, so that would be our amount at the end of that 5-year period if we want that first option. So $11,318 and let's say 23 cents. We'll round it to the nearest penny. Okay. If we go with the second option, we're using it compounded continuously. So that means we're going to use the other formula. That was that PERT formula up there. So for option 2, what we need is P. So P is still the $8,000 principal. We need R. Now the interest rate for the second option was 6.5%. So as a decimal, that's 0.065. And then we need T, which is still 5 years. So we're going to have A equals 8,000, E to the 0.065 times 5 power. And then we did put that into the calculator. So let's try that. Oops. Let's try that. See if we can get this to show up for you. Sorry, I know the picture is not great. We'll work on this in class as well so we can all get some practice with the calculator. So make sure you bring your calculators to class. Don't bring your cell phone, bring your calculator, because you're going to need to practice using the calculator you're going to use on the test. So we've got 8,000, and then I'm using that E key. So if I'm on the graphing calculator, the E key is right down here above the natural log key. So I'm going to do second E, and mine automatically puts the caret key up there to the 0.065 times 5. Make sure you use parentheses for those terms in your exponent. And we get an amount of $11,072. So let's write that down. So we're going to have $11,072, and it looks like about 25 cents. So if you're investing, which one sounds like a better deal? If you're the one that's doing the investing, you want to make more money, right, at the end of the 5-year period. So option 1, you had a little bit more in the account. So option 1 would have been the better deal in that scenario. The last question, we're looking at an example of a population question. So a lot of times we talk about population growth with people or animals, if you're talking about in biology class or something like that. We use exponential functions to model that. And so it says, suppose the population of an endangered species of wolf in a preserve area is modeled by the function f of x equals 1.26 e to the 0.0247 x power, where x is the years after 1985. The question is, what is the population expected to be in the year 2019? So they're asking us to find the population after a certain time period. So if we look at 2019, they said that x was the number of years after 1985. So how many years are there between 1985 and 2019? If we just subtract 2019, take away 85, we get a difference of I believe it's 34 years. So our x that we're going to use, we're going to plug into the equation 34 years, and we're going to calculate this to see what the wolf population is expected to be in 2019. So we're going to do f of 34 equals 1.26 e to the 0.024, oops, wait a minute, the zero is in front, so 0.247 times 34. So make sure you see what I got there. I've got 0.247 times 34 is my exponent. So again, we're going to go back to the calculator. And let's see if we can get this to show up here. We're using that E key again. Sorry about the glare. Let me move this over just a little bit. So we're going to do 1.26 and practice this, like I said, with your calculator, because you're going to need to know how to do this. 1.26 second natural log is the E key, 0.247 times 34 years. And so the population for the wolves is expected to be around 5,592. Now, they didn't give us units for the wolves, so this might be millions, this might be thousands. I don't know, but they didn't say it. I'm going to round it to the nearest whole number because we're talking about a wolf. We can't have part of a wolf, so we're going to round this to the nearest whole number. I'm just going to round down and say 5,592 wolves is what we'd expect in the year 2019.